Picture, for a moment, the most peculiar beach you have ever seen. There is no sun in the sky, only a perpetual, thick haze of deep red and orange. The air is so heavy and hot it feels like a physical weight, and the ground beneath your feet is scorching rock. Now look out at the ocean. It's not made of water, but a churning, superheated vapor. This is not a sea. It's a global ocean of steam, and as you stand there, you notice something truly bizarre falling from the alien sky. It's not water, not ice, but shards of glass whipped sideways by howling winds. This is not a scene from the most audacious science fiction film. This is a real place. An actual world orbiting a distant star, and its name is GJ1214b. It defies almost every expectation we have for what a planet can be. We often look to the stars and wonder about Earth-like worlds, planets of rock and water that feel like home. But the universe, it turns out, is far more imaginative than we are. It crafts worlds so alien, so utterly strange, that they force us to rethink the very fundamentals of planetary science. GJ1214b is one of those worlds, a steam planet that stands as a monument to cosmic diversity, a key that could unlock our understanding of an entire class of exotic planets hiding in the darkness between the stars. What makes a discovery like this so profoundly gripping is that it touches on something deep within us, the relentless human drive to explore the unknown, to push past the boundaries of the familiar and confront the truly extraordinary. For centuries, we could only guess at the nature of other worlds. Now, with our powerful telescopes and ingenious methods, we are not just guessing anymore. We are pulling back the veil on realities that once existed only in our dreams and nightmares. GJ1214b is a testament to that journey. It's a world that challenges our definitions, a place where the very states of matter we take for granted behave in ways that seem impossible. The idea of a steam ocean isn't just a poetic phrase. It's a scientific reality with staggering implications for chemistry, geology, and even the potential for life in forms we have not yet dared to conceive. As we begin our exploration today, we are going to do more than just list the facts and figures of this incredible world. We are going to take a journey to its surface to understand the forces that shaped it and the phenomenal conditions that make it so unique. We will uncover how scientists even found such a world so far away, and what its existence tells us about the incredible variety of planets that must be out there, waiting to be found. This is a story of human curiosity meeting cosmic wonder, a narrative that stretches from the silent data of a distant telescope to the breathtaking vision of a planet where the familiar rules of nature are rewritten. So, join me as we venture to this steam world, to explore one of the most enigmatic and fascinating places we have ever discovered beyond our solar system. The journey is just beginning. The story of this alien world begins not with a direct image, but with a subtle, repeated dimming of a faint, cool star. This detection was the work of the M-Earth project, a dedicated array of humble robotic telescopes perched atop Mount Hopkins in Arizona. Their mission was specific and revolutionary: to stare night after night at small, dim red dwarf stars, searching for the telltale sign of a planet crossing the face of its sun. This technique, known as the transit method, is like witnessing a microscopic eclipse from dozens of light years away. When a planet transits its star, it blocks a tiny, almost imperceptible fraction of the starlight. For a giant telescope staring at a single point, this dip is the universe whispering a secret. In 2009, M-Earth caught that whisper from a star called GJ1214, located 48 light-years from Earth in the sprawling constellation Ophiuchus, the Serpent Bearer. The data revealed a planet, soon named GJ1214b, and it immediately stood out for several astonishing reasons. First, its orbit is unbelievably fast. This world completes a full journey around its parent star in just 1.58 Earth days. To put that into perspective, a full year on this planet passes in less than 38 hours. You could celebrate your birthday twice every weekend. This blistering speed places it incredibly close to its star, but because that star is a small, cool red dwarf, the planet exists in a strange, temperate zone, not hot enough to be a hellish lava world like some, but not cold enough to be a frozen wasteland. This proximity, however, leads to another of its defining features, its size. The amount of starlight it blocks told astronomers this was no terrestrial planet like Earth or Mars. With a diameter about 2.7 times that of Earth and a mass nearly 6.6 times greater, GJ1214b falls into a category that was at the time entirely new to science. It's too large to be a rocky super-Earth, but too small to be a gas giant like Jupiter. This placed it squarely in the enigmatic class of mini-Neptunes, a type of world that doesn't even exist in our own solar system, suggesting it's likely shrouded in a deep, dense atmosphere. And this is where the story of GJ1214b truly ascended from a simple discovery to a landmark event. When the planet transits, starlight doesn't just vanish. A tiny fraction of that light filters through the planet's atmosphere before reaching our telescopes. Different gases in the atmosphere absorb specific colors of this light, leaving a chemical fingerprint in the starlight. When astronomers trained the powerful Hubble Space Telescope on this system, they successfully read that fingerprint. GJ1214b became one of the very first exoplanets of its size ever to have its atmosphere directly detected and studied. This wasn't just finding a new world, it was opening a window into its very sky, confirming that this distant sphere was enveloped in a thick, substantial shroud, turning it from a theoretical point of light into a tangible atmospheric world. This pioneering measurement set the stage for everything we would later theorize about its steamy, mysterious nature, proving that we could, in fact, begin to study the weather on planets orbiting distant stars. So we had the planet's location, its size, and its mass, but the most profound mystery remained. What was it actually like to be there? The answer lay in the secrets hidden within its atmosphere, and to uncover them, scientists turned to one of humanity's greatest tools for cosmic exploration, the Hubble Space Telescope. The method they used is as elegant as it is powerful. When GJ1214b passes in front of its star, a tiny sliver of starlight doesn't just hit the planet's solid surface or its cloud tops and stop. Instead, this light skimmed through the planet's atmospheric limb, filtering through the very gases that make up its sky before continuing on its 48 light-year journey to reach our telescopes. Think of it like holding a stained glass window up to the sun. The light that comes through on the other side isn't pure white. It's missing the specific colors that were absorbed by the pigments in the glass. In exactly the same way, every molecule in an atmosphere absorbs a unique fingerprint of light. Water vapor, methane, hydrogen. Each one leaves a dark bar in the rainbow of starlight, a telltale signature of its presence. With bated breath, astronomers directed Hubble's gaze toward this distant transit, collecting the filtered starlight and breaking it down into its constituent colors, searching for these chemical fingerprints. What they found, however, was not what anyone had quite expected. Instead of a spectrum rich with the deep, dark absorption lines of specific gases, the data revealed something much more uniform, a spectrum that was almost completely, perplexingly flat. Across a wide range of wavelengths, from the visible into the infrared, the starlight was being dimmed evenly. It was as if they were looking at a distant, hazy street lamp through a thick, blanketing fog the light gets through, but all its distinct colors are muted into a single, dull glow. This flat line was a revolutionary piece of data. It decisively ruled out the possibility of a clear, hydrogen-dominated atmosphere like that of Jupiter or Neptune. If that were the case, Hubble would have seen pronounced dips in the light, the unmistakable signatures of hydrogen and helium. The atmosphere of GJ1214b was something else entirely. It was an opaque, high-altitude shroud that was effectively masking whatever lay beneath. This finding pointed overwhelmingly to two compelling possibilities. The first was a global, permanent layer of clouds or a high-altitude haze, so thick and uniform that it prevented light from penetrating deep enough to probe the lower atmosphere. But these wouldn't be water clouds like those on Earth. At the immense temperatures and pressures on this world, scientists theorized they could be composed of something far more exotic, salts like potassium chloride or even hydrocarbons, similar to the smog that blankets some cities but on a planetary scale. The second, and even more captivating possibility, was that the atmosphere itself was not primarily hydrogen, but was instead what scientists term a water-rich or steam atmosphere. Imagine an entire planetary envelope not of thin air, but of incredibly dense hot water vapor. In such an atmosphere, the molecules are so packed together and the conditions so alien that they can create a natural, global opacity, a steamy veil that scatters light evenly, producing that very same flat spectrum Hubble observed. This was the moment the steam world hypothesis transformed from a speculative idea into a leading, evidence-backed explanation. We weren't just looking at a gas giant. We were potentially looking at the seething, vapor-filled sky of a planet-wide ocean, a place where the very air you breathe would be a scorching, suffocating fog. So, with this thick, opaque atmosphere confirmed, the central mystery became what lies beneath it. Is this a world with a solid surface at all, or is it something else entirely? This question propelled scientists into a fascinating detective story, piecing together clues from its mass, size, and atmospheric data to build competing models of its interior structure. The two leading theories paint dramatically different pictures of this alien world, and each comes with its own compelling evidence and significant challenges. The first and perhaps most captivating theory is that GJ1214b is a true water world. In this model, the planet has only a relatively small, dense core of rock and metal, perhaps not much larger than Earth. Enveloping this core is an absolutely staggering volume of water, making up a substantial fraction of the planet's entire mass. But here's the critical point. Due to the intense pressure from the overlying layers and the searing heat from the nearby star, this water isn't a tranquil, blue ocean as we know it. Instead, it's thought to exist in a series of extraordinary, exotic states. The uppermost layer would indeed be a superheated steam atmosphere that opaque shroud Hubble detected. As you journey downward, the pressure increases exponentially, forcing that vapor to condense into a global, planet-wide ocean of liquid water. But this is no placid sea. It would be a churning, supercritical fluid, a state where the distinction between liquid and gas blurs, possessing properties of both. Deeper still, the pressure becomes so immense that the water is compressed into strange, hot forms of solid ice. Not like the ice in your freezer, but high-pressure crystalline structures with names like Ice 6 and Ice 7. These are ices that form at temperatures far above the boiling point of water on Earth, locked into a solid state by the crushing weight of the ocean above them. This model neatly explains the planet's overall low density, which is consistent with a large fraction of light materials like water, and it provides a natural explanation for the flat atmospheric spectrum. The steamy upper layer itself acts as the obscuring veil. The alternative theory presents a very different kind of planet. This model suggests that GJ1214b is at its heart a mini-Neptune. It would possess a sizable rocky core, but instead of a deep water ocean, it is swaddled in a massive primordial envelope of hydrogen and helium gas, the same fundamental ingredients from which the giant planets in our solar system formed. In this scenario, the thick, opaque atmosphere Hubble saw isn't made of steam, but is instead a global, permanent layer of high-altitude clouds or a photochemical haze that completely blocks our view. What kind of clouds could they be? At the temperatures on this world, they wouldn't be made of water. Scientists have proposed that they could be composed of tiny particles of zinc sulfide or salts like potassium chloride, condensing high in the atmosphere much like water clouds do on Earth, but creating an impenetrable reflective barrier. The challenge for this model is explaining the flat spectrum without any signs of hydrogen. Proponents suggest that the haze particles are simply so efficient at scattering light that they mask the underlying hydrogen-rich atmosphere completely, a phenomenon we see to a lesser extent on worlds like Saturn's moon, Titan, which is shrouded in an orange hydrocarbon haze. Each of these theories has its own set of puzzles to solve. For the Waterworld model, a major question is one of origins. How did a planet so close to its star acquire and retain such an enormous quantity of water? Water is a common molecule in the universe, but forming a world that is more water than rock in the hot inner region of a star system is a complex challenge for planetary formation theories. It might have formed further out in the colder reaches where ice is abundant, and then migrated inward to its current location. For the mini-Neptune model, the primary hurdle is the lack of a hydrogen signal. Creating and maintaining a cloud layer so perfectly uniform and opaque that it completely hides the spectroscopic signature of the most common element in the universe is a tall order, requiring a very specific and stable atmospheric chemistry. Ultimately, the true nature of GJ1214b likely lies somewhere on a spectrum between these two extremes. It could be a hybrid world, a so-called gas dwarf, with a moderate hydrogen envelope over a deep layer of water, or a core that is a mix of rock and ice. This ongoing scientific debate is a perfect example of how a single, enigmatic world can force us to refine our models and consider possibilities we never imagined, revealing just how diverse planetary systems can be. Now let's journey deeper into this alien ocean, descending into a realm where the very definition of water becomes alien. If the Waterworld theory is correct, the ocean covering GJ1214b is not a single uniform body. Instead, it's a world of layers, a tiered structure of increasingly bizarre states of matter, each one more alien than the last. Picture a dive that starts in a superheated steam atmosphere, a fog so dense it blots out the sky. As you press downward, the first major transition occurs. The crushing weight of the atmosphere above forces the vapor to condense, not into rain, but directly into a global ocean of liquid water. But this is no ordinary sea. The surface temperature of this ocean is estimated to be hundreds of degrees. On Earth, water at such temperatures would exist only as a gas, but here, the pressure is so immense thousands of times greater than the atmospheric pressure at Earth's sea level that the water cannot boil. It is trapped in a liquid state, but a profoundly strange one. At a certain depth, the heat and pressure cross a critical threshold, and the water enters a state known as a supercritical fluid. In this phase, the familiar distinction between liquid and gas completely vanishes. This supercritical water would have the density of a liquid but the diffusive properties of a gas, creating a churning, chaotic medium where chemical reactions could occur with ferocious speed, a seething, featureless abyss unlike anything found on our planet. The true marvel, however, awaits you even deeper. As you continue this descent into the abyss, the pressure climbs to almost incomprehensible levels, reaching millions of times Earth's surface pressure. It is here, in the profound darkness near the ocean floor, that the water undergoes its most radical transformation. It freezes, but this is not freezing as we understand it. You are surrounded by water at temperatures of several hundred degrees Celsius, yet under this astronomical pressure, the water molecules are forced into a rigid, crystalline lattice. They form solid ice. This is the realm of what scientists call the exotic, high-pressure phases of ice, Ice 6, Ice 7, and beyond. These are not the familiar, fluffy ice one we know. They are dense, hot solids with crystal structures that are more compact and orderly, forged in an environment where the very concept of cold is meaningless. You would be swimming, or rather, trying to navigate through a landscape of solid, hot ice, a substance that behaves like rock but is chemically identical to the water in your glass. This layer of hot ice would form a strange, slushy mantle, sitting directly atop the planet's rocky core, a final, frozen frontier in a world defined by its liquid and vapor envelope. To grasp just how alien this is, consider the phases of water on Earth. We have one common solid phase, ice 1. GJ1214b, by contrast, could potentially host several different high-pressure ice phases stacked atop one another, each with its own unique crystalline structure and properties. This isn't a single state of matter. It's a whole portfolio of water's behavior under extremes we can only replicate fleetingly in specialized laboratories. This exotic interior has profound implications. It means the planet could have a seafloor made of ice, not rock, fundamentally altering how we think about planetary geology and the potential for geothermal activity. Any heat flowing from the rocky core below would have to pass through this insulating layer of hot ice before it could reach the liquid ocean and the steam atmosphere above, potentially creating a far more stable and layered environment than we might first assume. The existence of such a place shows us that the universe has a much richer catalog of materials and environments than our experience on Earth suggests, crafting worlds where the most common molecule in the cosmos can build structures of almost poetic strangeness. Stepping through that dense, steamy atmosphere and finally reaching what we might call the surface would reveal a landscape of almost biblical extremity. The first thing to strike you would be the heat, an oppressive, omnipresent force. With an average surface temperature estimated around 230 degrees Celsius or 446 degrees Fahrenheit, the environment is far hotter than any oven you would find in a kitchen. This isn't merely a hot day, it's a temperature where many metals would begin to soften and where the very concept of comfort is rendered meaningless. This infernal heat is trapped by a phenomenal greenhouse effect driven by the enormous pressure of the atmosphere itself. We talk about atmospheric pressure in terms of bars, with one bar being the pressure at sea level on Earth. On GJ1214b, the pressure could be hundreds of times greater. You wouldn't simply feel this as a weight on your shoulders, you would experience it as a physical compression, a sensation of the entire world pressing in on you from all directions, making every movement a monumental effort and every breath, if breathing were possible, an act of drawing in a suffocatingly dense, hot fluid. Above this scorching surface, the sky would present a perpetual, deep twilight. The parent star, GJ1214, is a dim red dwarf, and while it looms larger in the sky than our Sun does from Earth due to the planet's close orbit, its light must first filter through that global shroud of steam and haze. The result is a sky that is never truly bright. Imagine a diffuse, dull red glow emanating from all directions, with no distinct point of origin for the light. There is no sharp sunrise or sunset, no blue sky, and certainly no view of the stars. The cloud deck is so thick and permanent that it turns the sky into a featureless, glowing dome of deep crimson and burnt orange, casting the entire landscape in an eerie, monotonous light. This star itself would appear as a bloated, dark red orb, its faint light stained even deeper by the absorbing atmosphere, bathing everything below in a somber, hellish palette. This unearthly red illumination would fall upon a world with no oceans or continents as we know them. If the planet is a water world, the surface might be the top of that superheated liquid ocean, a seething, rolling plain of water perpetually at the brink of boiling, yet held in a liquid state by the immense atmospheric pressure. There would be no waves crashing against a shore because there would be no shore, only a global, steamy sea fading into a hot, red haze at the horizon. If the planet has a solid surface beneath the atmosphere, it would be a global desert of scorched, molten rock, perhaps slick with condensing exotic fluids from the atmosphere, constantly eroded by the unimaginable weather. And speaking of weather, the conditions would be ferocious. The extreme temperature difference between the permanent day side and the permanent night side, if the planet is tidally locked, could drive supersonic winds circulating that dense atmosphere in a violent planet-wide torrent. The rain here wouldn't be water. At these temperatures, it could be molten silicate or droplets of liquid metal condensing out of the vapor, falling sideways in scorching, glass-filled hurricanes. This is not a world of subtle beauty, but one of raw, elemental power, a testament to the violent and diverse processes that shape planets under the most extreme conditions imaginable. But let's pause for a moment on that idea of a permanent global cloud deck, because the very nature of these clouds is one of the most fascinating puzzles this planet presents. What could they possibly be made of? On Earth, clouds form when water vapor cools and condenses into tiny liquid droplets or ice crystals. But on GJ 1214b, with surface temperatures soaring past 200 degrees Celsius, water in its familiar liquid or ice form simply cannot exist in the atmosphere. Any water present would be a superheated vapor, part of that steamy shroud. So, the clouds that scientists believe are creating this opaque veil must be composed of something far more exotic, something that can condense at these incredible temperatures. The leading candidates are not substances we typically associate with weather, but with the stuff of chemistry sets and industrial processes. One compelling possibility is that the high atmosphere is laced with a fine mist of salts, specifically potassium chloride. Think of table salt, but instead of sodium chloride, it's a different compound that vaporizes at high heat and then, as it rises and cools slightly in the upper atmosphere, condenses back into tiny, glittering crystals. These wouldn't be snowflakes, they would be more like a pervasive, hot dust, reflecting and scattering light uniformly to create that flat spectrum Hubble observed. Another candidate is zinc sulfide, a compound that on Earth is used in luminescent paints and some semiconductors. On this alien world, it could exist as a high-altitude smoke, a photochemical haze generated by the intense, though faint, ultraviolet light from the red dwarf star breaking down other molecules in the atmosphere. This process is not entirely unlike the one that creates the thick, orange hydrocarbon smog on Saturn's moon Titan, but operating at a much higher, more blistering temperature. This leads us to an even more dramatic speculation. Some models suggest that at the extreme temperatures found on the day side of this tidally locked world, the conditions could be hot enough to literally vaporize rock. Silicate rocks, the very foundation of terrestrial planets, could be heated until they release vapors of minerals like enstatite or forsterite into the atmosphere. As these mineral vapors rise and are carried by winds to the slightly cooler regions of the planet, perhaps the terminator line between day and night, or the permanent night side, they would condense out not as rain, but as a mist of liquid rock droplets or fine, glassy dust. Imagine for a moment standing under a sky where the clouds are not made of water, but are a scorching fog of vaporized rock and metal, occasionally precipitating as a sideways rain of molten silica. This isn't a water cycle, it's a rock cycle, a geological process playing out in the atmosphere with a ferocious intensity we can scarcely comprehend. The existence of such clouds fundamentally changes how we view planetary atmospheres. It demonstrates that a planet's climate is not just about temperature and pressure, but about the available chemistry. The sky on GJ 1214b is not just an envelope of gas. It is a giant, roving chemical laboratory where elements and compounds undergo phase changes that are utterly alien to our earthly experience. These clouds aren't merely obscuring our view, they are an active and dynamic component of the planet's identity, a testament to the fact that under the right, or rather the extreme, conditions, even the ground beneath your feet can take to the skies, creating weather systems of truly astronomical proportions. When we talk about weather on Earth, we think of rain, snow, and winds that, while powerful, operate within a familiar range of physical laws. On GJ 1214b, the very concept of weather is rewritten into something far more extreme and alien, driven by one fundamental and inescapable feature of its orbit: tidal locking. Just as our moon always shows the same face to Earth, this planet is almost certainly locked to its star, meaning one hemisphere is bathed in permanent, searing daylight while the other is plunged into an endless, frigid night. This setup creates a temperature gradient of almost unimaginable severity. The day side, constantly baked by the faint but close red sun, might simmer at several hundred degrees Celsius. The night side, conversely, could plummet to temperatures colder than Antarctica, a deep freeze shrouded in darkness. This colossal difference doesn't just create a mild breeze, it acts as a colossal planetary engine, driving atmospheric circulation on a terrifying scale. The superheated, dense air on the day side would expand and rush upward with tremendous force, screaming toward the cold vacuum of the night side. Meanwhile, the cold, heavy air on the night side would sink and flow back along the surface toward the day side to replace the rising column. This creates a permanent, planet-wide torrent of wind, a maelstrom in the sky that could easily reach supersonic speeds, whipping that thick, steamy or hazy atmosphere into a frenzied, continuous hurricane encircling the entire globe. The precipitation on this world would be something out of a metallurgist's dream or perhaps nightmare. Forget water droplets, the constituent materials available to form clouds and rain here are the very stuff of rock and salt. On the scorching day side, where temperatures could be high enough to literally vaporize certain types of silicate rock, the lower atmosphere might be rich with mineral vapors. As these vapors are caught in the global wind patterns and carried to the marginally cooler terminator region, the twilight line between day and night, they wouldn't have far to travel before crossing a critical condensation threshold. Here, the vaporized rock would condense directly into a mist of tiny, molten droplets. This wouldn't be a gentle drizzle, it would be a scorching, sideways rain of liquid silica and other minerals, a storm of rock falling from a sky of steam. On the slightly cooler night side, or at higher altitudes where temperatures drop, the condensation could form snow, but not snow as we know it. If the clouds are indeed made of salts like potassium chloride or zinc sulfide, these particles could solidify into hot, crystalline flakes. Imagine a blizzard of salt falling through a dense crimson haze, its particles glittering in the dim, red starlight before plunging into the superheated ocean or dissolving back into the turbulent atmosphere below. This is a weather cycle built not on water, but on geology and chemistry, where the sky itself participates in a slow, violent process of planetary refining. The sheer density of the atmosphere amplifies every one of these phenomena into something truly monumental. With surface pressures potentially hundreds of times greater than on Earth, the air on GJ1214b is less like a gas and more like a thick, viscous fluid. This means the supersonic winds, while not possessing the same shredding force they would in a thin atmosphere, would still exert an immense, crushing pressure on anything in their path. The sound of these winds would be a constant, low-frequency roar, a vibration felt through the entire planet's structure rather than a noise heard in the conventional sense. The precipitation, too, would be transformed by this density. Falling droplets of molten rock or flakes of salt would encounter immense aerodynamic resistance, likely making them very small and causing them to fall slowly, perhaps even being carried aloft again for great distances by the powerful updrafts. This could create permanent, global storms of suspended particulate matter, a swirling, opaque cocktail of mineral dust, salt crystals, and superheated steam that never truly settles, forever painting the sky in a uniform, featureless veil that hides the planetary surface from our telescopes and completes the planet's enigmatic and forbidding character. This remarkable state of eternal day and night is known as tidal locking, a gravitational tug of war that has profoundly shaped the planet's destiny. The mechanism is a familiar one, seen right here in our own cosmic backyard with our moon, which always shows us the same face. For a planet like GJ-1214b, orbiting so incredibly close to its star, the star's gravitational pull is immensely powerful. This force acts like a brake, gradually slowing the planet's rotation over millions of years until it perfectly matches its orbital period. The result is that one hemisphere, the day side, is forever locked in a blazing, unending noon, while the opposite hemisphere, the night side, is trapped in an eternal, starless midnight. This isn't merely a quirk of its orbit, it is the single most important factor determining its climate, its weather, and the very structure of its atmosphere, creating a world of two utterly alien and distinct realms. The contrast between these two hemispheres is almost beyond human comprehension. On the permanent day side, the feeble red light of the star GJ-1214 beats down relentlessly. While the star itself is dim, the sheer constancy of the irradiation, combined with the thick, heat-trapping atmosphere, cooks the surface to temperatures that could melt lead, likely soaring well above 200 degrees Celsius. This is not a desert, it's a furnace. The global cloud deck, whether made of steam or exotic salts, would be a permanent feature here, but beneath it, the ground, or the top of the superheated ocean, would be simmering at the maximum temperature the system can sustain. There is no cooling night, no seasonal change, only this perpetual, oppressive heat. The very rocks on the surface, if any exist, might be warm enough to glow a dull red in the deepest crevices, and the atmosphere itself would be a churning, superheated fluid, expanding violently under the intense thermal energy. Journey to the night side, and you enter a realm of a different, yet equally extreme nature. With no incoming starlight for billions of years, you might expect this hemisphere to be frozen solid. And while it is certainly far colder than the day side, the reality is more complex and in some ways even more forbidding. The incredible atmospheric pressure and density on GJ-1214b act as a massive thermal blanket. Heat from the day side isn't easily radiated away into space. Instead, it is efficiently transported by the planet's furious winds. This means the night side, while profoundly dark and cold, is likely still hundreds of degrees hotter than any place on Earth. It would be a landscape or seascape of profound darkness where the only faint glow might come from atmospheric airglow or the dim, reflected heat from the day side on the cloud base above. Any surface here would be steadily cooling, but the relentless influx of hot air from the day side prevents it from ever approaching true cryogenic freezing. It is a world of two extremes, but they are extremes of heat, not of heat and cold, a crucial distinction that shapes the planet's entire meteorology. This radical temperature disparity sets the stage for a weather system of almost unimaginable violence. The fundamental driver of all weather is a difference in energy, and GJ-1214b possesses the most powerful engine imaginable. The superheated air on the day side expands, becoming less dense and soaring upward in a planet-wide convective column. To replace this rising air, cold, dense air from the night side rushes in along the surface. But this is no gentle sea breeze, this is a planet-spanning torrent. The pressure difference between the two hemispheres is so immense that scientists calculate these winds could consistently roar at thousands of kilometers per hour, far exceeding the speed of sound. These aren't winds as we experience them. They are a continuous supersonic shockwave of atmosphere, circulating the planet in a desperate attempt to balance the unbalanceable. This atmospheric river doesn't just move air, it is the planet's primary method of heat distribution. The supersonic winds act as a global conveyor belt, constantly dragging the incandescent air from the day side and hurling it into the dark abyss of the night, while simultaneously pulling the cooled air back toward the light. This process likely prevents the night side from solidifying entirely and keeps the day side from heating up to even more astronomical temperatures. The point where these two colossal air masses meet, the terminator line, would be a region of permanent colossal storm fronts. Here, the screaming winds from opposing directions collide, creating turbulence and weather phenomena so vast and powerful they would dwarf the great red spot of Jupiter. It is along this tempestuous boundary that we might see the most exotic precipitation, where mineral vapors carried from the hot daytime suddenly condense into a searing, horizontal rain of molten glass and rock, a storm of geological fury raging in perpetual twilight. This relentless global circulation is the heartbeat of the steam planet, a testament to the raw physical forces that dominate worlds living on the gravitational edge. To truly understand the forces shaping this steamy world, we must turn our gaze upward to the source of its light and heat, its parent star. GJ 1214 is not a star like our Sun. It is a red dwarf, a small, dim, and incredibly common type of star that makes up the vast majority of stellar residents in our galaxy. These stars are frugal with their fuel, burning so slowly that they can shine for trillions of years, far outliving any other stellar type. But this longevity comes with a hidden, violent temper. Red dwarfs are notoriously unstable, especially in their youth. They are frequently rocked by immense stellar flares, sudden, explosive releases of magnetic energy that can cause the star's brightness to double or even triple in a matter of minutes. These aren't gentle flickers, they are cataclysmic eruptions that blast the surrounding space with intense doses of high-energy radiation, particularly in the ultraviolet and X-ray part of the spectrum. For a planet like GJ 1214b, orbiting so astonishingly close that its year is less than 2 days long, it is living directly in the line of fire, constantly bathed in a harsh, sterilizing glow that has profound consequences for its atmosphere and its future. This relentless bath of high-energy radiation from the star acts like a cosmic blowtorch, systematically attacking the planet's atmospheric envelope. The process is known as atmospheric escape, and it works by giving atoms and molecules in the upper atmosphere so much energy that they can achieve escape velocity, breaking free of the planet's gravity and streaming off into space. Ultraviolet photons are particularly effective at this. When they strike molecules, they can break them apart into individual atoms and then heat those atoms to tremendous temperatures, creating a seething, high-altitude layer of plasma. For a hydrogen-rich atmosphere, this process can be a death sentence, slowly bleeding the planet of its lightest and most abundant element over billions of years. But for GJ 1214b, the situation is more complex and, in a way, more revealing. The very fact that the planet still possesses such a thick, substantial atmosphere today, despite billions of years of this relentless bombardment, is a powerful clue. It strongly suggests that what we are seeing is not a primordial, lightweight hydrogen envelope, which would be relatively easy to strip away, but something much denser and more massive, like that deep, steamy ocean or a heavy, hazy shroud. A massive water vapor atmosphere, for instance, would be far more resistant to this type of erosion, its heavier molecules much harder for the star's radiation to push into space. This ongoing struggle between the planet's gravity and the star's wrath is a key factor in the world's long-term evolution. Imagine two possible futures dictated by the initial inventory of the planet. In one scenario, if GJ 1214b started its life as a classic mini-Neptune with a large, puffy envelope of hydrogen, the persistent stellar flares may have been slowly but surely peeling that atmosphere away like the layers of an onion. Over the eons, this could have transformed the planet, potentially leaving behind a denuded, rocky core, a world that began as a gas dwarf and ended as a scorched, airless sphere. In the alternative scenario, if the planet truly is a water world from the start, the story is different. The intense ultraviolet radiation would still be relentlessly breaking apart water molecules in the upper atmosphere, splitting H2O into hydrogen and oxygen. The lightweight hydrogen would be the first to be lost to space, while the heavier oxygen might be retained, potentially creating a new, secondary atmosphere or being sequestered into the ocean and rocks below. This process could fundamentally alter the atmospheric chemistry over geological time, perhaps even creating an oxygen-rich atmosphere not through biology, as on Earth, but through the harsh, abiotic photolysis driven by its tempestuous sun. When we consider the possibility of life, the role of this active red dwarf star becomes a central and largely pessimistic factor. The very conditions that create the potential for liquid water, the planet's location in the star's so-called habitable zone, are the same conditions that expose it to a brutal and unending radiation storm. The frequent, powerful flares would not only threaten to erode the atmosphere but would also bathe the surface, or the upper ocean, in doses of UV and X-rays that would be instantly lethal to life as we know it. Any hypothetical organism would need to be shielded by an immense depth of water or buried deep within the hypothesized hot ice crust to survive. Furthermore, a planet that is tidally locked presents another challenge for habitability. While our previous discussion highlighted the powerful winds that distribute heat, the permanent darkness of the night side and the permanent, direct irradiation of the day side create two extraordinarily extreme environments, with the most temperate region likely being a narrow, violent strip of eternal twilight at the terminator line, constantly scoured by those supersonic winds and exotic precipitation. This paints a picture of a world where the basic requirements for life, a stable, temperate environment and protection from lethal radiation, are incredibly difficult to meet, pushing the very definition of habitability to its absolute limit and forcing us to consider just how tenacious and strange life would have to be to gain a foothold in such a furnace. When Hubble revealed that curiously flat spectrum from GJ1214b, it did far more than just describe a single, strange world. It handed astronomers a master key, a Rosetta Stone for deciphering the atmospheres of an entire class of planets we had only just begun to discover. Before this, our knowledge of exoplanet atmospheres was largely confined to bloated, scorching giants planets like HD 209-458b, a world so inflated by stellar heat that its atmosphere could be easily probed. Studying these giants was like trying to learn about all forests by examining only the tallest redwood trees. GJ1214b represented something entirely different, a smaller, denser world that fell into the mysterious gap between Earth and Neptune. Its flat transmission spectrum became the essential reference point, the defining example of what astronomers now call a featureless or flat spectrum. This wasn't an absence of data, it was a new category of data, a powerful signature that immediately ruled out a whole family of atmospheric models and forced the community to think more creatively. Suddenly, a flat line in the data wasn't a failed observation. It was a positive detection of something complex and obscuring, a challenge that would push telescope technology and theoretical modeling to their very limits. This single measurement fundamentally shifted the questions we asked about distant worlds. Instead of simply wondering what gases are in this atmosphere, scientists were now compelled to ask what is hiding the gases in this atmosphere. GJ1214b demonstrated that for many small exoplanets, the most interesting part of the story might not be the clear primary composition, but the complex high-altitude layer of aerosols, whether clouds or haze, that acts as a planetary veil. It taught us that a planet's climate cannot be understood by its bulk properties alone. You must account for the intricate microphysics of cloud formation in alien environments, where the condensing materials could be salts, sulfides, or even organic soot. This realization sparked a mini-revolution in atmospheric modeling. Researchers began to develop sophisticated new computer simulations that could incorporate the formation, distribution, and optical properties of these exotic particulates. They had to move beyond the simple, clear atmosphere models that worked for gas giants and build tools capable of simulating a global, permanent shroud. The planet became a critical testbed, a benchmark against which these new models could be validated. If a model could successfully reproduce the flat spectrum of GJ1214b, it gained credibility for interpreting the more ambiguous data we would collect from other, even more distant worlds. The technical legacy of this world is equally profound. Its successful study proved that the Hubble Space Telescope, even when pushed to the absolute edge of its capabilities, could perform this delicate type of measurement on a planet smaller than Neptune. This achievement provided the crucial proof of concept that gave astronomers the confidence to design the next generation of space observatories, most notably the James Webb Space Telescope, with the explicit capability to conduct these atmospheric studies on a much larger scale and with far greater precision. GJ-1214b was the pathfinder, the trailblazer that showed it was possible. It created the observational and data processing protocols that are now standard practice. Astronomers learned how to carefully subtract the stellar signal, how to account for instrumental noise, and how to extract the exquisitely tiny whisper of light that had filtered through an alien sky. Every small, rocky planet whose atmosphere we hope to characterize with James Webb owes a debt to this pioneering STEAM world, which proved that such a daring measurement was not just a fantasy, but a feasible, albeit incredibly difficult, scientific reality. In the grand narrative of exoplanet science, GJ-1214b occupies a pivotal role as a transitional object. It sits right in the middle of the size gap between terrestrial planets and ice giants, a category that is surprisingly common in our galaxy but completely absent from our own solar system. Its intense study taught us that this mini-Neptune class is not a single type of world, but likely a diverse family with a spectrum of possible structures, from water worlds with steamy envelopes to gas dwarfs with hydrogen-rich atmospheres obscured by haze. By forcing us to consider this diversity, it shattered any lingering notion that our own solar system was a template for the galaxy. We learned that the most common type of planet in the universe might be one for which we have no local example, a world that is neither rocky like Earth nor gaseous like Jupiter, but something uniquely in between. GJ-1214b, with its enigmatic flat spectrum, became the archetype for this mysterious class, the first one we truly got to know, and in doing so, it redefined our cosmic perspective, showing us that the universe is not just full of planets, but full of planetary possibilities we are only beginning to imagine. To truly appreciate the otherworldly nature of GJ-1214b, let's bring it home quite literally by placing it side by side with our own familiar planet. The differences are not just degrees of variation, they are fundamental shifts in the very definition of a world. Consider their physical dimensions. Our Earth, with its diameter of just under 13,000 kilometers, is a benchmark for rocky planets. GJ-1214b is a substantially larger sphere, its diameter about 2.7 times that of Earth. While that might not sound colossal in planetary terms, it's a dramatic difference, putting its volume at nearly 20 times that of our world. Yet its mass is only 6.6 times greater. This math reveals the first and most crucial distinction. Earth is a dense ball of rock and metal, while GJ-1214b is overwhelmingly light and fluffy. Its average density is less than 2 grams per cubic centimeter, only about a third of Earth's density, and not much more than that of pure water. This single number shatters the image of a rocky twin and immediately points toward a composition dominated by vast quantities of lighter elements, likely a massive ocean or a thick, gaseous shroud, making it a planet built from entirely different materials. This fundamental divergence in composition leads to an atmospheric experience that defies earthly comparison. Our atmosphere on Earth is a remarkably thin and delicate blanket. At sea level, we experience a comfortable pressure of about 1 bar, a mix of nitrogen and oxygen that is transparent, breathable, and relatively gentle. The atmosphere of GJ-1214b is a crushing, oppressive entity. Its surface pressure is estimated to be hundreds of times greater than Earth's. Stepping onto its surface would not feel like stepping into a storm. It would feel like being at the bottom of a deep ocean, with the very air pressing in with the weight of a colossal, invisible column of fluid. And unlike our clear, nitrogen-rich sky, its atmosphere is a permanent opaque fog, potentially a superheated steam or a haze of exotic salts that scatters light into a uniform, dull glow, utterly obscuring any view of the cosmos or even its own sun. The temperature regimes of these two worlds highlight their opposing places in the cosmic spectrum of habitability. Earth enjoys a delicate, life-sustaining balance with a global average temperature around 15 degrees Celsius. This allows for the stable existence of liquid water, frozen ice, and water vapor, the three familiar phases that drive our climate and biology. On GJ1214b, that balance is violently skewed. With an average temperature soaring around 230 degrees Celsius, it exists in a state of perpetual, scorching heat. This isn't merely a hotter version of a summer day, it's a temperature where the very states of matter change. Liquid water can only exist under immense pressure, and the concept of ice refers not to cold crystals, but to hot, high-pressure solid phases that form in the abyssal depths. The planet's entire climate is dictated by this infernal heat, creating weather patterns that are not just more intense, but of a completely different nature altogether. Their orbits around their respective stars further cement their alien relationship. Earth orbits our Sun at a comfortable, temperate distance of 1 astronomical unit, taking a leisurely 365 days to complete its journey. This stable, nearly circular orbit gives us predictable seasons and a reliable day-night cycle, fundamental pillars for the evolution of complex life. GJ1214b, in stark contrast, is locked in a dizzying, intimate dance with its dim red dwarf star. It completes a full orbit in just 1.58 Earth days, meaning a year passes in less than 38 hours. This proximity has almost certainly led to tidal locking, creating a world with a permanent day side of blistering, unending daylight and a permanent night side of profound, starless darkness. There are no seasons, no sunrises, and no true nights as we know them, only a stark, eternal division between a furnace and a shadow, a radical departure from the rhythmic cycling that defines life on our own planet. Ultimately, this comparative exercise does more than just list differences. It fundamentally expands our definition of what a planet can be. Our solar system presented us with a seemingly simple taxonomy: small, rocky inner planets and large, gaseous outer giants. GJ1214b, a world that is both massive and light, both scorching and shrouded, defies this neat categorization. It represents a whole new class of celestial body, the mini-Neptune or water world, that is incredibly common in our galaxy but absent from our own cosmic neighborhood. By studying its profound contrasts with Earth, we learn that the term planet is not a specific blueprint but a broad category encompassing an astonishing diversity of environments. It teaches us that our own world, with its gentle climate and thin, clear air, is not the standard model for a planet, but rather one special, fragile case in a cosmos filled with worlds of steam, of rock vapor, and of hot ice, each one a testament to the universe's boundless capacity for invention. So, with all these fantastically hostile conditions laid bare, we arrive at the ultimate, haunting question: could this steamy, alien world somehow harbor life? On the surface, the answer seems to be a resounding and definitive no. The surface temperatures are hundreds of degrees above the boiling point of water, the atmospheric pressure is crushing, the sky rains molten glass, and the entire planet is bathed in sterilizing ultraviolet radiation from its flare-happy star. For any life form resembling what we find on Earth reliant on liquid water, a narrow temperature range, and complex organic molecules, GJ1214b is not just inhospitable. It is a roaring, planetary-scale furnace designed to dismantle biological complexity. The surface, whether it is a seething ocean or scorched rock, is a realm of pure physical extremity where the very chemistry of life as we know it would fall apart instantly. Yet, the history of science is a chronicle of discovering life in places we once deemed utterly lifeless. Here on Earth, we have found thriving ecosystems in the most unexpected and severe environments. The deep-sea hydrothermal vents, for example, are sunless, high-pressure worlds where superheated, mineral-rich water erupts from the ocean floor. There, in the eternal darkness, entire communities of organisms, from giant tube worms to bizarre, heat-loving bacteria, flourish not by photosynthesis but by chemosynthesis. They draw their energy not from the sun, but from the chemical potential of sulfur and other compounds spewing from the planet's interior. This discovery fundamentally expanded our understanding of life's requirements, proving that light and a gentle climate are not universal prerequisites. All that is truly needed is a source of energy, a liquid medium for chemical reactions, and a suite of essential elements. This radical perspective forces us to look at a world like GJ1214b, not just for its surface horrors, but for any potential sanctuary where these basic conditions might be met, no matter how deep or dark. If the water world model is correct, the most compelling refuge for life would not be anywhere near the hellish surface, but in the profound depths of its global ocean. Imagine a hypothetical ecosystem not in the sunlit shallows, but anchored to a hypothetical hydrothermal vent on the ocean floor, a place buried under hundreds of kilometers of a bizarre tiered ocean. The surface layers above would be a superheated, supercritical fluid, but as we descend, the pressure climbs to millions of times that of Earth. Eventually, we would reach a boundary, not a seafloor of rock, but a strange, slushy mantle of hot, high-pressure ice. It is at the interface between this hot ice layer and the true, rocky core of the planet where our most tantalizing possibilities emerge. Geological activity within the rocky core, warmed by the decay of radioactive elements or residual formation heat, could very well drive hydrothermal systems. These would not be gentle springs, but vents erupting with incredible force, pumping heat and dissolved minerals from the planet's interior up into the deep, dark ocean above. In this abyssal refuge, the surface's greatest threats would be rendered moot. The crushing pressure, while immense, is a constant, stable condition that life could potentially adapt to, just as deep-sea creatures on Earth thrive under hundreds of atmospheres of pressure. The lethal ultraviolet radiation and stellar flares from the red dwarf star would be completely absorbed and scattered by the hundreds of kilometers of dense ocean and steam above, creating a perfectly shielded environment. The violent, supersonic weather of the upper atmosphere would be nothing more than a distant, muffled rumble, if it was perceptible at all. The primary challenge for life here would be the intense heat, but even that might not be insurmountable. The water near the rocky core would be extremely hot, but the circulation of the ocean could create thermal gradients, much like those around Earth's deep-sea vents, providing micro-environments where temperatures could fall within a range that some extremophile organisms could tolerate. The energy for life would not come from the absent sun, but from the chemical disequilibrium provided by the vent fluid's hydrogen sulfide, methane, and other reduced minerals reacting with the ocean's chemistry. In this eternal darkness, life could potentially exist as a thin, tenuous film clinging to the underside of a ceiling of hot ice, a biosphere utterly isolated from the universe above, thriving on the planet's internal geothermal heartbeat. However, the obstacles to such a scenario are monumental and force us to confront the limits of biochemical possibility. One of the most significant barriers is the potential presence of that layer of exotic, solid ice between the liquid ocean and the rocky core. If this ice mantle is global and completely solid, it would act as an impenetrable barrier, severing the crucial chemical connection between the rocky core's nutrients and the liquid ocean above. The ocean would become a closed system, its chemical energy sources eventually depleted, with no way to be replenished from the planet's geological engine. For life to be possible, this ice layer would likely need to be porous or punctuated by areas of melt, allowing for some form of chemical exchange between the core and the ocean, a process that is purely speculative and for which we have no earthly analog. Furthermore, the very stability of complex organic molecules under such extreme temperatures and pressures is unknown. While life on Earth has pushed the boundaries of heat tolerance, the conditions at the base of this alien ocean might simply be too extreme for the delicate structures of proteins and genetic material to hold together, no matter how alien their biochemistry might be. Ultimately, the question of life on GJ 1214b remains one of the most profound and open-ended in modern astrobiology. It serves less as a promising candidate for discovery and more as a philosophical and scientific boundary marker. This steam planet challenges us to stretch our definition of a habitable environment to its absolute breaking point, to consider biospheres that are not surface-dwelling and sunlit, but deep, dark, and utterly isolated. It teaches us that when we search for life elsewhere, we must look beyond Earth-like surface conditions and peer into the hidden depths of worlds, considering the possibility of ecosystems that are completely independent of their star, powered solely by the slow, geological warmth of the planet itself. While the chances are slim, the mere possibility that life could cling to existence in such a fantastic and hostile environment expands our sense of cosmic wonder, reminding us that life, if it exists out there, may be far more ingenious, resilient, and strange than we have ever dared to dream. The decades-long mystery surrounding the true nature of this distant world is now on the verge of a spectacular resolution, all thanks to a new eye in the sky that is fundamentally rewriting the rules of astronomical observation. The James Webb Space Telescope, with its unprecedented sensitivity and powerful suite of infrared instruments, represents a quantum leap in our ability to probe the secrets of exoplanets like GJ 1214b. Where the Hubble Space Telescope gave us our first crucial glimpse, revealing a flat, featureless spectrum that pointed to a shrouded world, Webb is equipped to see straight through that veil. Its mission is to transform that enigmatic flat line into a rich, detailed chemical fingerprint, finally answering the foundational question: are we looking at a global steam ocean or a cloud-obscured mini-Neptune? This isn't just an incremental improvement, it's the difference between seeing the silhouette of a person through a frosted glass window and being able to clearly distinguish the color of their eyes and the expression on their face. The key to this revolutionary capability lies in Webb's design, which is optimized for the infrared part of the light spectrum. Many molecules, especially those central to the debate over this planet, have their most pronounced and identifiable absorption features in the infrared. Water vapor, methane, ammonia, carbon dioxide, each one leaves a unique barcode in the infrared light that filters through a planetary atmosphere. Hubble's view was limited, like trying to read only a few pages of a long book. Webb, by contrast, can read the entire volume, scanning a much broader and more diagnostic range of wavelengths with stunning precision. When GJ 1214b transits its star, Webb will capture the minuscule fraction of starlight that passes through its atmospheric limb, not with a broad brush, but with a fine-tipped scalpel, dissecting the light to reveal the hidden signatures of specific chemicals that have remained invisible to us until now. So, what exactly will the telescope be searching for? The primary target, the molecule that could single-handedly confirm the water world hypothesis, is unsurprisingly water. But Webb won't just be looking for a simple, faint signal. In a thick, steam-rich atmosphere, the water vapor signature should be exceptionally strong and deep, a dominant feature that could overwhelm other, subtler signals. A clear, unambiguous detection of vast quantities of water vapor would be a monumental piece of evidence, strongly tilting the scales toward the model of a planet with a deep, global ocean shrouded in steam. Conversely, if Webb detects a different suite of gases, such as a significant amount of ammonia or methane alongside the water, that would powerfully support the mini-Neptune model. These gases are expected to be abundant in hydrogen-rich atmospheres, the kind a gas dwarf would possess. Finding them would suggest we are looking at a world with a substantial primordial envelope, where the obscuring clouds are made of exotic salts or hazes, hiding the hydrogen-dominated atmosphere below. Perhaps the most exciting prospect is Webb's potential to detect what are known as spectral windows. Even the thickest planetary hazes can become transparent at certain specific wavelengths of infrared light. Webb's sophisticated instruments like NIRSpec and MIRI are perfectly designed to hunt for these narrow gaps in the cloud cover. If such a window is found, it would be like a sudden break in a global fog bank, allowing the telescope's gaze to pierce through to the deeper, hotter layers of the atmosphere. The chemical composition revealed at those depths would be the ultimate decoder ring. Measurements from these deeper layers could provide a direct reading of the atmosphere's mean molecular weight, a fundamental property that distinguishes a heavy, water-rich atmosphere from a light, hydrogen-dominated one. This single measurement could effectively solve the mystery, providing a definitive answer that decades of theoretical modeling have been unable to conclusively provide. The implications of this impending discovery extend far beyond a single strange world. GJ1214b is the archetype, the prototype for an entire class of common but mysterious planets. By definitively classifying this world, Webb will provide a critical benchmark for understanding the entire population of mini-Neptunes and super-Earths in our galaxy. Is this a water world, suggesting that many planets in this size range are fundamentally oceanic, perhaps having migrated inward from the cold, icy outer regions of their star systems? Or is it a gaseous dwarf, indicating that small planets can readily acquire and retain thick hydrogen envelopes, making them fundamentally different from any planet in our solar system? The answer will guide how astronomers interpret the sparse data from thousands of other distant worlds, allowing them to better predict which ones might be genuine water-rich oases and which are simply small gas balls. This is the power of the James Webb Space Telescope. It turns points of light into real, tangible worlds with known properties, bringing us one giant step closer to understanding our true place in a galaxy teeming with planetary wonders. The struggle to decode the flat spectrum of GJ1214b was far more than an academic exercise focused on a single world. It fundamentally forged a new set of tools and a deeper understanding that is now accelerating our entire search for life beyond Earth. The great challenge this planet presented, a world whose atmosphere was utterly masked by a high-altitude veil, forced astronomers to move beyond simple models and develop sophisticated new techniques for seeing what is, by definition, hidden. The methods honed and the lessons learned while wrestling with its steamy or hazy shroud have created a universal playbook, a diagnostic framework that is now being applied to dozens of other mysterious exoplanets. When we point our most powerful telescopes at a distant world and see that same perplexingly flat spectrum, we no longer shrug in confusion. Instead, we recognize a familiar signature. We understand we are likely looking at a planet with a high-altitude layer of aerosols, and we can immediately begin using the analytical toolkit built for GJ1214b to determine whether those aerosols are likely steamy water, exotic salts, or hydrocarbon hazes. This planet taught us how to ask the right questions of the data, transforming a dead end into a new, well-marked path forward in exoplanet atmospheric science. This hard-won expertise is not just for understanding bizarre steam planets or mini-Neptunes. It is absolutely foundational for the next great leap in astronomy, the search for signs of life on Earth-sized worlds orbiting within the habitable zones of their stars. Consider for a moment what a true Earth twin might look like from dozens of light years away. It wouldn't be a serene blue marble with clearly defined continents. Our own planet, when observed in a transit, would present a spectrum significantly muted by its extensive cloud cover. Those beautiful white water vapor clouds that drift through our sky would act as a natural veil, scattering starlight and complicating the detection of the very gases that signal life: oxygen, methane, and ozone. Without the prior experience of dissecting the opaque atmosphere of GJ1214b, we might look at the spectrum of a genuinely habitable Earth-like planet, see a somewhat flat or muted signal, and mistakenly dismiss it as a featureless, uninhabitable world, or worse, completely misinterpret its atmospheric composition. The work on this steamy planet taught us how to model the effects of clouds and hazes with incredible precision, allowing us to subtract their obscuring effects from the data and peer through to the chemical signatures beneath. It showed us that a flat spectrum isn't a stop sign. It's a detour that requires a more clever and determined route to the truth. The technological and analytical legacy of GJ1214b is therefore directly encoded into the operational plans for our most advanced future observatories. The James Webb Space Telescope's observations of small, cloudy exoplanets are using data processing pipelines and atmospheric retrieval models that were rigorously tested and refined on the data from this very world. When Webb turns its gaze toward a potentially habitable planet around a red dwarf star, the team of scientists analyzing the data will be using algorithms that were essentially trained on the difficult case of GJ1214b. They will know how to look for the subtle spectral windows where cloud cover becomes thin, how to interpret the relative strengths of different molecular bands in the presence of haze, and how to use the shape of the spectrum itself to estimate the altitude and composition of the obscuring particles. This is not a trivial contribution. It is the difference between having a blurry, indecipherable photograph and having a sophisticated image enhancement tool that can clarify details you never knew were there. The planet acted as a universal calibration target, a complex puzzle that, once solved, gave us the master key for unlocking countless other atmospheric mysteries. Ultimately, the story of GJ1214b is a powerful reminder that the most frustrating scientific challenges often yield the most broadly useful breakthroughs. Its stubborn refusal to reveal its secrets easily compelled us to build better models, design more sensitive observation strategies, and think more creatively about planetary diversity. The tools forged in the effort to understand its steamy shroud are now part of the standard arsenal for characterizing any small, cool exoplanet. As we enter an era where we will discover thousands more planets in habitable zones, many of which will likely be cloudy, the legacy of this enigmatic steam world will ensure we do not overlook a potentially life-bearing signature simply because it is hidden behind a veil. It taught us to be better, more perceptive cosmic detectives, proving that the key to finding life elsewhere in the galaxy may very well have been forged in the intense, steam-driven atmosphere of one of the strangest worlds we have ever known. This journey into the strange conditions of GJ1214b opens up an even broader and more exciting cosmic possibility. What if this world, for all its current hostility, represents just one version of a much more common and potentially life-friendly type of planet? This brings us to the fascinating concept of the Haitian world, a term born from blending the words hydrogen and ocean. Imagine a planet larger than Earth but smaller than Neptune, swaddled in a thick, hydrogen-rich atmosphere and possessing a vast globe-spanning liquid water ocean on its surface. In many ways, this description fits one of the leading models for GJ1214b almost perfectly. If this distant steam planet does indeed possess a substantial hydrogen envelope over a deep water layer, then it isn't just a singular oddity. It becomes a scorching, high-pressure prototype for an entire class of worlds that astronomers are now actively hunting. The key difference is one of location and temperature. Where GJ1214b orbits so close to its star that its water ocean would be a superheated, supercritical fluid, a true Haitian world would reside further out, within its star's habitable zone, where temperatures would allow for a vast, stable, and liquid ocean to exist beneath that atmospheric shroud. The potential habitability of these Haitian worlds is what makes them such a compelling subject of study. At first, a planet with a hydrogen atmosphere might seem like the last place you would look for life. We think of our own delicate balance of nitrogen and oxygen as the only recipe for a living world. But scientific models suggest that a hydrogen-rich atmosphere could be surprisingly effective at creating a stable, temperate environment. This thick hydrogen envelope would create a powerful greenhouse effect, trapping heat from the star and distributing it efficiently across the planet. More importantly, it would exert immense pressure on the surface, a characteristic that is actually crucial for the Haitian concept. This high pressure would prevent a liquid water ocean from boiling away, even at temperatures significantly higher than the boiling point on Earth. This expands the traditional definition of the habitable zone, suggesting that planets orbiting farther from their stars than an Earth-like world could still maintain liquid water, thanks to the pressure from their hydrogen blankets. In this scenario, a planet like GJ1214b is not a sterile furnace, but a Haitian world that simply orbits too close to its sun, a hot, extreme cousin of a potentially life-bearing family. The idea of life thriving under such a sky forces us to rethink biochemistry itself. We are accustomed to life that breathes oxygen, but many of the most ancient microorganisms on Earth are perfectly capable of living in anaerobic or oxygen-free environments. On a Haitian world, life would not use oxygen for respiration. Instead, it could potentially metabolize using the abundant hydrogen or other chemicals dissolved in the ocean, much like the microbes that thrive around deep-sea hydrothermal vents on our own planet. The ocean itself, shielded from harmful stellar radiation by the thick hydrogen atmosphere and miles of water, would provide a stable, global sanctuary. While the surface might be whipped by winds and devoid of solid land, the ocean depths could be remarkably calm and rich with the chemical energy needed to power a biosphere. The immense pressure, which seems so alien and crushing to us, would simply be the normal condition for any life that evolved there, shaping its cellular structures and biological processes in ways we can only begin to imagine. GJ1214b, in its current state, is far too hot for this, but it serves as a vital laboratory for understanding the atmospheric and oceanic physics that would govern its more temperate siblings throughout the galaxy. This connection places GJ1214b at the very heart of a modern astronomical quest. It acts as a crucial benchmark, a nearby example we can study in detail to validate the models we use to understand planets we may only get a fleeting glimpse of. When astronomers use the James Webb Space Telescope to search for biosignatures, the atmospheric gases that might be produced by life, on distant, temperate Haitian candidates, the data and experience gained from studying GJ1214b will be their essential guide. They will know what to look for and, just as importantly, what might be hidden. The same high-altitude hazes that obscure our view of this steam planet could also shroud a life-bearing Haitian world, and learning how to peer through that veil here gives us the tools to do it elsewhere. The discovery of a single, strange world 48 light-years away has thus given us a template for an entire category of planets that might be among our best bets for finding life beyond Earth. It demonstrates that the universe may have many different paths to creating habitable environments, and some of the most promising ones could be these enigmatic, water-rich worlds cloaked in a deep hydrogen sky. Given the vast distance and the thick veil shrouding this world, you might wonder how we can claim to know anything about its deep oceans or supersonic winds. We cannot travel there, and no probe has ever sent back a picture. The answer lies in one of the most powerful tools of modern astrophysics, the supercomputer simulation. Here on Earth, scientists are building digital twins of GJ1214b, constructing entire virtual planets inside powerful computing clusters to test our theories against the cold, hard data from our telescopes. This process is a continuous cycle of prediction and refinement, a digital dialogue between human imagination and cosmic reality. It begins with the fundamental physics we understand: the laws of gravity, thermodynamics, fluid dynamics, and chemistry. Researchers code these universal rules into sophisticated software, creating a virtual laboratory where they can assemble a planet from scratch. They set initial parameters: a planet of a certain mass and radius, orbiting a specific type of star at a precise distance. Then they hit run, and the supercomputer brings their theoretical world to life, calculating the complex interactions of its atmosphere, the circulation of its heat, and the very structure of its interior over billions of simulated years. These models are not simple animations. They are mathematical universes governed by millions of lines of code solving intricate equations simultaneously. To simulate the global climate of a tidally locked world like GJ1214b, for instance, the planet's surface and atmosphere are sliced into a three-dimensional grid. Each cell in this vast digital lattice represents a parcel of the planet, with the supercomputer constantly calculating the temperature, pressure, density, and velocity for every single one, and how each cell influences its neighbors. The sheer scale of these calculations is staggering, requiring some of the most powerful processors on the planet to simulate just a few days of planetary time. These models must account for the absorption and scattering of starlight by the steamy atmosphere or exotic hazes, the transfer of heat from the scorching day side to the frigid night side, and the formation of clouds from condensing salts or silicates. It is a computational ballet of phenomenal complexity, all aimed at producing a synthetic version of the planet that can be compared to the one we indirectly observe. The true test, however, comes when we bring the virtual face to face with the actual. The ultimate purpose of these sprawling simulations is to generate a prediction of what our telescope should see if the model is correct. For GJ1214b, the most critical observational data is that flat, featureless transmission spectrum from the Hubble Space Telescope. So, after a supercomputer completes a simulation of, say, a water world with a deep steam atmosphere, scientists don't just look at the pretty visuals of its weather. They calculate how starlight would filter through that specific simulated atmosphere. They ask, does our digital planet produce a spectrum as flat as the one Hubble actually measured? If the answer is yes, the model gains credibility. If the simulated spectrum shows deep absorption features that are absent in the real data, the model is either refined or discarded. This is how that enigmatic flat spectrum became such a powerful constraint. It immediately ruled out entire families of models, particularly those with clear, hydrogen-dominated atmospheres, and forced modelers to focus on scenarios involving high-altitude clouds or a substantial water vapor envelope. The real-world data acts as a cosmic referee, judging the countless digital worlds we create and guiding us toward the ones that most closely resemble reality. This iterative process of modeling and comparison is how we probe the very interior of the planet. The models for the internal structure are different from the climate models, but they work on the same principle. Scientists start with the two most fundamental pieces of data we have: the planet's mass and its radius. From these, we can calculate its average density, which tells us it cannot be made of rock alone. The modelers then create a range of possible interior structures: a small rocky core with a massive water layer, a larger rocky core with a moderate hydrogen envelope, or a hybrid gas dwarf with a mix of both. For each hypothetical structure, they use equations of state complex formulas that describe how materials like rock, water, and hydrogen behave under extreme pressure and heat to predict the planet's overall radius. The model that predicts a radius matching the one we actually observe becomes the leading candidate, but even here, the atmosphere plays a crucial role. The climate models and the interior models are deeply linked. The thickness and composition of the atmosphere influence the planet's thermal evolution and even its apparent size. A single observation, therefore, ripples through every layer of our theoretical understanding, from the uppermost haze down to the hypothesized mantle of hot ice, forcing a consistency across all our models that makes the final picture far more robust and credible. This dynamic interplay between hard scientific data and boundless creative imagination is what truly brings a world like GJ 1214b into the public consciousness, transforming it from a distant data point into a vivid, living landscape. Long before the James Webb Space Telescope was even a blueprint, artists and science communicators were grappling with the same fundamental mystery that challenged astronomers. What does this world actually look like? Armed with the sparse but tantalizing clues from Hubble and other observatories, they set to work, and their resulting visualizations have become the primary lens through which we all experience this alien planet. These aren't just pretty pictures, they are hypotheses rendered in color and form, each one a carefully considered argument about the nature of reality based on the best available evidence. One school of thought, championing the Waterworld model, paints a scene of breathtaking, if terrifying, beauty. In these depictions, the viewer stands on a surface of shimmering, superheated liquid, a global ocean that rolls with a strange, heavy viscosity under the oppressive weight of the atmosphere. The sky is a uniform, glowing dome of deep crimson and burnt orange, a perpetual twilight created by the thick steam shroud. There are no stars, no sun, only this eerie, diffuse light reflecting off the choppy, simmering sea. These artworks capture the profound loneliness and immense scale of a planet that is all ocean, a world where the very horizon curves away into a steamy oblivion, inviting us to contemplate the mysteries hidden beneath its turbulent, hot waves. In stark contrast, the artistic interpretations based on the mini-Neptune hypothesis present a completely different kind of alien majesty. Here, the artist envisions a world with a solid surface, but one that is forever hidden beneath a global, impenetrable layer of cloud. The sky in these renditions is often a swirling, textured tapestry of yellows, oranges, and reds, suggesting a high-altitude haze of exotic salts or hydrocarbons. The lighting is similarly dim and diffuse, but the feeling is less of a steamy bath and more of a dusty, ancient smog. Some of these illustrations dare to imagine a glimpse below the cloud deck, portraying a rocky landscape under a towering, opaque ceiling, with strange, viscous fluids perhaps trickling down mineral formations. Others focus on the upper atmosphere itself, showing colossal, slow-moving vortexes and jet streams in the cloud tops, hinting at the supersonic winds raging below. This artistic division perfectly mirrors the scientific debate, giving the public not one, but two equally compelling and plausible visions of the same distant world. By presenting these competing possibilities, science communicators do a profound service. They visually demonstrate that science is a process of inquiry, not a set of fixed answers, and that some of the most exciting discoveries are those that still hold onto their secrets. The impact of these visualizations extends far beyond mere illustration. They are powerful engines of public engagement and inspiration. For a generation growing up with the knowledge that planets orbit other stars, these artists' concepts are their first postcards from these new frontiers. A child looking at a stunning depiction of GJ 1214b's steamy ocean isn't just seeing a cool picture. They are being invited on a journey, their curiosity sparked by the sheer alienness of the scene. This visual connection makes abstract scientific concepts tangible and emotionally resonant. It's one thing to read that a planet has a high-altitude haze. It's quite another to see a digital painting of a vast, rocky plain under a swirling, orange sky, with a large, dim red star peeking faintly through the thick haze. This transformation of data into landscape makes the science accessible to everyone, regardless of their technical background. These images adorn websites, textbooks, and planetarium shows. They are shared millions of times on social media, and they feature prominently in documentaries, forming the visual backbone of the modern narrative of cosmic exploration. They answer the fundamental human question: what would it be like to be there? And in doing so, they create a sense of wonder and ownership over these distant discoveries, making the public feel like they are part of the grand adventure of exploration. This creative process is also a deeply collaborative one, a continuous dialogue between the artist and the scientist. The most respected space artists don't work in a vacuum. They spend countless hours consulting with the research teams, understanding the nuances of the data, the constraints of physics, and the leading theoretical models. They ask questions like, if the atmosphere is primarily steam, how would that affect the way light scatters? Or, what color would zinc sulfide clouds be under the light of a red dwarf star? This back and forth ensures that the final artwork, while imaginative, remains scientifically plausible. It's a form of translation, taking the complex language of spectra, albedos, and chemical abundances and translating it into a visual scene that the human brain can instantly comprehend and appreciate. The artist becomes a bridge between the raw data of the telescope and the public imagination, a critical interpreter in the chain of scientific communication. Their work ensures that the excitement of a discovery is not lost in a fog of technical jargon, but is instead amplified and broadcast to the world in a form that is both beautiful and intellectually honest. Ultimately, the diverse gallery of images depicting GJ1214b serves as a powerful reminder of the role of the unknown in driving science forward. The fact that we can have two such dramatically different, yet equally valid artistic interpretations for a single planet is a testament to the tantalizing incompleteness of our current knowledge. This ambiguity is not a failure, it is the very fuel of scientific progress. The beautiful, haunting uncertainty captured in these paintings and digital renders is what motivates the next observation, funds the next telescope, and inspires the next generation of scientists and engineers. They are a visual representation of a question mark, and in that question lies all the promise of future discovery. As we await the definitive answers from the James Webb Space Telescope, these artistic visions stand as monuments to human curiosity, proving that our drive to explore is matched only by our power to imagine, and that sometimes the most important tool for understanding the cosmos is not just a telescope but a paintbrush. Now let's pull back the curtain for a moment and be completely transparent about the monumental challenge that studying a world like this truly represents. We've painted a vivid picture of steam oceans and glass rain, but it's crucial to understand that every single detail we've discussed comes to us across a mind-boggling chasm of 48 light years. To grasp the scale of this feat, imagine trying to discern the precise composition of a fog bank hanging over a city from a vantage point dozens of miles away, using only a telescope that can barely see the city's lights. That is the essential nature of our quest to understand GJ1214b. The planet itself is not just small. From our perspective, it is a microscopic speck, a tiny dark pixel transiting a star that is itself a mere point of light in our sky. The dip in brightness we measure during a trance, it is almost vanishingly small, often less than 1% of the star's total light. Detecting that signal at all is a triumph of modern engineering and data analysis, but trying to then split that already minuscule amount of light into a rainbow of colors to read its chemical fingerprints is an exercise in pushing technology to its absolute breaking point. The primary obstacle, the one that defines this entire investigation, is that pervasive global veil. The thick clouds or steamy haze that enshroud the planet are not merely a feature of its weather. They are an active participant in a cosmic game of hide and seek. When we use the transit method to study an atmosphere, we are fundamentally relying on starlight to pass through that atmosphere. In an ideal scenario with a clear, cloud-free sky, the light penetrates all the way down to the planet's surface or deep cloud decks, interacting with a rich soup of molecules that each leave their unique mark. But on GJ1214b, the light doesn't get that far. It hits this high-altitude shroud and is scattered, reflected, or absorbed before it can probe the interesting chemistry happening below. It's the difference between being able to look through a clean window into a room and trying to see through a wall of thick, frosted glass. The flat spectrum we observe is the direct result of this. It's the scientific signature of a door being slammed shut, telling us in no uncertain terms that our view of the lower atmosphere and any potential surface is almost completely blocked. This fundamental limitation forces scientists to rely heavily on inference, sophisticated modeling, and a process of elimination. Since we cannot see what is beneath the veil directly, we must use the clues we can gather to rule out what it cannot be. The flat spectrum, for instance, immediately eliminated the possibility of a clear, hydrogen-dominated atmosphere. That was a huge step forward, but it left open multiple, equally plausible possibilities: the steam atmosphere versus the salt cloud scenario. Choosing between them with the data from Hubble was like trying to determine the contents of a locked safe by only listening to the sounds it makes when you shake it. You might be able to guess if it contains something heavy and solid or something lighter and shifting, but you cannot know for sure if it's gold bullion or a collection of ball bearings without opening it. Our current understanding is built upon this kind of careful, deductive reasoning, where we construct entire planetary models and then see which ones are compatible with the few precious data points we have managed to collect. This inherent uncertainty is what makes the study of exoplanets both so frustrating and so exhilarating. We are operating at the very edge of detection, where the signal is barely distinguishable from the random noise inherent in the instruments and the shimmering of our own atmosphere. A single measurement can take many hours of precious telescope time, and the results often require months of painstaking analysis and statistical validation to confirm that what we are seeing is a real feature of the planet, and not just a flicker in the starlight or an artifact of the telescope's electronics. It is a field built on patience and persistence, where grand, sweeping conclusions about alien worlds must be built one tiny, fragile piece of evidence at a time. The story of GJ1214b is a powerful testament to human ingenuity, showing that even when the universe presents us with its most stubbornly guarded secrets, we can still find ways to ask the questions and develop the tools to one day find the answers. Looking billions of years into the future of this steamy world reveals a fate dictated by the slow, profound evolution of its parent star. Red dwarfs like GJ1214 are the ultimate cosmic marathon runners, burning their hydrogen fuel with such miserly frugality that their lifetimes are measured in trillions of years, far longer than the current age of the universe itself. This extraordinary longevity might seem to promise stability, but for a planet orbiting so close, it's a guarantee of relentless, slow-burn transformation. Unlike our Sun, which will one day swell into a red giant and engulf the inner planets, this dim red star will simply cool and dim over near infinite eons. As its fiery youth of violent flares gives way to a vastly long, quiet middle age, the primary force shaping the planet's destiny will shift from stellar tantrums to a more subtle, yet equally ruthless process: the irreversible loss of its atmosphere to the vacuum of space, a slow leak that could ultimately define its final state. This process, known as atmospheric escape, is a battle of attrition between the planet's gravity and the star's persistent influence. Even as the star's flaring activity subsides over billions of years, it will continue to emit a steady stream of ultraviolet and X-ray radiation. For a planet like GJ1214b, this high-energy light acts like a constant, slow-acting solvent on the upper layers of its atmosphere. Photons strike atmospheric molecules, breaking them apart and heating the remaining atoms to tremendous speeds. If these particles gain enough kinetic energy to exceed the planet's escape velocity, they simply fly off into the void, never to return. The rate of this loss isn't explosive. It's a geological drip, drip, drip of the planet's very sky being stripped away atom by atom. The ultimate outcome of this multi-billion-year exodus depends almost entirely on what the planet is made of today. If it is a classic mini-Neptune with a puffy, lightweight hydrogen envelope, this process could be devastatingly effective. Over time, the vast primordial shroud of gas could be peeled away layer by layer, leaving behind a starkly different world, a barren, exposed core of rock and metal, a scorched and airless relic of its former self. However, if the water world hypothesis is correct, the planet's fate could be far more complex and strangely poetic. A deep, global ocean enveloped by a dense steam atmosphere presents a much more formidable challenge to stellar erosion. Water molecules are far heavier than hydrogen, making them much harder for the star's radiation to accelerate to escape velocity. The process would be slower, and the story would be one of chemical transformation as much as simple loss. The relentless ultraviolet light would still be breaking apart water vapor in the upper atmosphere, splitting H2O into hydrogen and oxygen. The lightweight hydrogen, once freed, would be the first to bleed away into space. But the heavier oxygen atoms would likely be retained by the planet's gravity. Over astronomical timescales, this could lead to a profound atmospheric makeover. The planet could slowly develop a secondary atmosphere rich in molecular oxygen, not as a product of life as on Earth, but as a stark, abiotic byproduct of its own slow destruction. This oxygen might then interact with the surface or ocean, perhaps creating a world with a rust-colored, oxygen-rich sky above a churning, high-pressure sea, a bizarre chemical state we have no analog for in our own solar system. The planet's ultimate end, trillions of years from now, is tied to the final, dark chapter of its star's life. After exhausting its hydrogen fuel, the red dwarf will eventually contract into a white dwarf, a super-dense, Earth-sized ember that will slowly cool to black over many more billions of years. During this transition, the star will lose mass, causing its gravitational grip on its planetary system to weaken. This could cause the orbits of any surviving planets to slowly drift outward. If GJ1214b has managed to retain any substantial atmosphere by this distant epoch, the cessation of the stellar wind and intense UV radiation from the now dark white dwarf might finally grant it a measure of peace. It could become a frozen, ice-shrouded world, its former steamy oceans frozen solid into a new crust of conventional ice over the ancient, high-pressure ice layers below. Alternatively, if its atmosphere has been completely stripped, it will remain a silent, dark cinder of rock and metal, circling the ghost of its star in perpetual, frigid darkness, a stark monument to the fleeting nature of planetary atmospheres and the relentless forces of cosmic time. The story of this one world, from its steamy, vibrant youth to its frigid, silent old age, mirrors the life cycle of planets across the galaxy, reminding us that even the most seemingly permanent worlds are merely temporary arrangements of matter in the unending flow of the cosmos. Beyond the hard data and scientific models, a world as profoundly alien as GJ1214b serves as a powerful catalyst for the imagination, inviting us to explore not just what is, but what could be. This is where rigorous science gracefully hands the baton to creative speculation, inspiring narratives that bridge the gap between known physics and the boundless realm of possibility. Science fiction has always used such exotic settings as a stage to examine the human condition, and the unique environmental pressures of this steam planet offer a fresh, almost unimaginable backdrop for such stories. Imagine a future where humanity, having mastered interstellar travel, dispatches a dedicated probe on a one-way mission into that perpetual crimson haze. This wouldn't be a sleek, graceful vessel, but a heavily armored, pressure-hardened sphere, designed to survive a descent through an atmosphere that behaves more like a fluid than a gas. The drama of such a story wouldn't lie in epic battles, but in the tense, silent struggle of engineering against an overwhelming environment. We could witness the probe's systems groaning under the immense pressure as it sinks deeper, its sensors blinded by the opaque shroud until it finally breaches the cloud layer to behold the sight below, a churning global ocean of superheated water under a sky of eternal, glowing twilight. The narrative tension would come from the sheer alien majesty of the discovery and the probe's fragile fight to transmit its findings back to awaiting humanity before being crushed or dissolved in the corrosive, high-temperature chemistry of this strange sea. Within that hypothesized global ocean, the potential for life forms of crystalline beauty and profound strangeness offers a treasure trove for speculative biology. Life on Earth is carbon-based and relies on water as a solvent, but on GJ-1214b, the rules are rewritten by extreme pressure and heat. What if life there isn't based on fragile, water-filled cells, but on intricate, stable silicate structures? Picture ecosystems not of flesh and blood, but of delicate, glass-like organisms that filter nutrients from the supercritical fluid around them. These beings might grow with the slow, geological patience of a crystal, their metabolisms powered not by sunlight, but by the planet's own internal geothermal heat or by chemical energy from hydrothermal vents on the seafloor. Their forms could be breathtakingly beautiful spiraling towers of living glass or floating, Medusa-like creatures whose transparent bodies shimmer with internal bioluminescence, lighting up the abyssal darkness. A science fiction story could explore the profound challenge of communication with such entities. How do you converse with a life form that thinks on a timescale of centuries, whose very concept of existence is tied to immense pressure and stasis rather than movement and rapid change? An encounter with this kind of radically different biology would force us to confront the narcissism of our own definitions of life, suggesting that consciousness and complexity could arise in forms so alien we might not even recognize them as alive at first glance. The planet's bizarre layered structure itself could serve as the foundation for an epic, vertical odyssey. A narrative could follow a crew of explorers navigating a vessel capable of withstanding the transition from the steamy atmosphere through the supercritical ocean and down to the strange realm of the hot ice mantle. Each layer would present a new world, a new ecosystem, and new physical laws to contend with. The journey through the supercritical ocean could be a voyage through a featureless, churning void, where navigation is impossible and the crew must rely on sonar to avoid strange, floating silica forests or immense, slow-moving leviathans. Penetrating the boundary into the hot ice crust would be like diving into a planet-sized geode, navigating crystalline caves and canyons under unimaginable pressure. Perhaps the most profound discovery wouldn't be life, but the fossilized remains of a previous spacefaring civilization that also found this world, their ruins preserved perfectly in the clear, hot ice, a chilling monument to the rise and fall of intelligence in the cosmos. Such a story taps into the deepest human drives for exploration and discovery, while using the planet's scientifically grounded extremes to create a sense of wonder and peril that is both fantastical and plausible. On a more philosophical level, the mere existence of GJ-1214b challenges our anthropocentric view of the universe. A science fiction narrative set here could powerfully explore themes of human insignificance and the sheer, indifferent power of nature. A lone research station clinging to a buoyant platform on the planet's ocean would be the most isolated outpost imaginable, its inhabitants living under a sky that offers no comfort, no familiar constellations, only a perpetual, dull red glow. The psychological impact of such an environment would be immense, fostering a new kind of cosmic loneliness. The story could delve into how human consciousness adapts or fractures when removed from every familiar environmental cue, from the day-night cycle to the color blue. The planet itself becomes a character, an antagonist that is not malicious but simply overwhelmingly other. It forces the characters, and by extension the audience, to accept that the universe is not designed for our comfort or comprehension. This steam world, in all its violent majesty, becomes a mirror reflecting our own small place in a cosmos that is far stranger, more diverse, and more magnificent than we ever conceived. reminding us that the greatest discovery might not be finding life out there, but finding a new perspective on life right here. Perhaps the most enduring legacy of this steamy world isn't just in the academic journals, but in its profound power to inspire the next generation of explorers, scientists, and dreamers. GJ 1214b has become a cornerstone of modern astronomy education, a familiar celestial landmark in textbooks, documentaries, and planetarium shows worldwide. Its unique combination of accessibility and sheer weirdness makes it the perfect gateway exoplanet, a compelling case study that educators use to introduce students to the revolutionary methods and breathtaking discoveries of modern planet hunting. Think about it, before the 1990s, our solar system was the only example we had. Teaching planetary science was like teaching art history with only 8 paintings, all from the same artist and the same period. GJ 1214b shattered that limited gallery. It's a tangible, well-studied example that proves our galaxy is teeming with worlds that defy our simple categories, offering educators a concrete, data-rich story to tell, moving the classroom discussion from abstract theory to thrilling, tangible reality. In the classroom, this planet serves as a masterclass in the scientific method itself. It beautifully illustrates the entire cycle of discovery, from the initial detection by the M-Earth Project's small, ground-based telescopes to the sophisticated atmospheric follow-up with the Hubble Space Telescope. Teachers can walk students through the entire detective story, how the subtle, repeating dimming of the star first revealed the planet's existence and orbit, how the depth of that transit gave us the planet's size, and how the gravitational wobble of the star, measured by other instruments, provided its mass. With these two fundamental pieces of data, students can perform the same calculations as professional astronomers, calculating the planet's density and immediately realizing that it cannot be made of rock alone. This hands-on engagement turns abstract equations into a real-world puzzle. Then comes the brilliant twist in the plot, the Hubble data. That flat, featureless spectrum becomes a classic scientific cliffhanger. It's not a failed observation, it's a crucial clue that demands creative interpretation. Students are forced to become planetary detectives, weighing the evidence for a steamy ocean against a world shrouded in exotic salt clouds, learning that in cutting-edge science, the most exciting answers are often the ones that raise the most profound new questions. This planet's educational value is amplified by its perfect storm of favorable characteristics. Its relative proximity of 48 light-years makes it a nearby target, at least on the cosmic scale, allowing our telescopes to gather enough light for detailed study. It orbits a small, dim star, which means the proportion of light it blocks during a trance. It is much larger and easier to detect than if it orbited a bright, sun-like star. Furthermore, its incredibly short orbital period of just over a day and a half means transits happen frequently, giving astronomers, and by extension, students, multiple opportunities to observe and gather data. It's a perfect pedagogical specimen. When educators want to explain complex techniques like transmission spectroscopy, they don't start with a faint, distant world that provides a weak signal. They start with GJ 1214b, the quintessential example of a small exoplanet with a detectable atmosphere. It demonstrates that these incredible measurements are not just theoretical fantasies, but achievable scientific practices, demystifying the tools we use to explore the cosmos and making the process accessible and exciting for young minds. The planet's impact extends far beyond the classroom lecture, finding a vibrant home in public outreach and popular science. It has become a staple of documentary filmmaking, its dramatic and alien nature providing a visual anchor for explaining exoplanet science to a global audience. CGI renderings of its steaming oceans and crimson skies have become iconic, translating complex data into breathtaking visuals that spark wonder and curiosity. In planetarium shows, a flight to GJ 1214b is often a highlight, immersing audiences in the sensory experience of this strange world in a way that graphs and spectra alone cannot. For the casual science enthusiast browsing the internet, articles and videos about this STEAM world are often their first introduction to the idea that planets can be so much more diverse than the ones in our own solar system. It serves as a powerful hook, drawing people into the broader story of exoplanet discovery and helping to build public support for ambitious and expensive next-generation missions like the James Webb Space Telescope. By capturing the public imagination, GJ1214b does more than just educate. It creates a culture of cosmic curiosity, reminding everyone that the universe is a place of endless wonder and discovery. Ultimately, GJ1214b's role as an educational gateway is a testament to its power as a narrative. It's not just a collection of data points, it's a story with a beginning, a mystery, and an ongoing quest for resolution. It embodies the human drama of science, the initial discovery, the surprising results, the competing theories, and the technological innovation required to solve the puzzle. This narrative arc makes it incredibly relatable. Students and the public aren't just memorizing facts, they are following a story. They become invested in the outcome, eager to learn what the James Webb Space Telescope will reveal. This transforms astronomy from a static list of facts into a dynamic, unfolding adventure, showing that our understanding of the cosmos is a living, evolving process. By serving as this perfect introductory world, GJ1214b plays a crucial role in shaping the future of science, inspiring the very people who will one day build the next great observatory, develop the next revolutionary theory, or perhaps one day pilot the first probe to a steamy world orbiting a distant star. Despite all we have learned, GJ1214b remains one of the most captivating enigmas in our cosmic catalogue, a world that continues to guard its deepest secrets with a stubborn persistence. Years of intense observation and sophisticated modeling have brought us to the edge of understanding, only to leave us staring into a fascinating fog of unresolved possibilities. The central, defining mystery that still hangs over this distant sphere is the true nature of its interior. Is it, at its heart, a genuine water world with a relatively small rocky core buried beneath a staggering volume of water in various exotic states? Or is it a fundamentally different kind of planet, a so-called gas dwarf or mini-Neptune, dominated by a thick, primordial atmosphere of hydrogen and helium that is simply hidden from our view by an impenetrable blanket of clouds? This is not a minor distinction. It is the difference between a planet that is fundamentally an ocean and a planet that is fundamentally a ball of gas. The data we have from its mass and radius allows for both scenarios, and each model requires its own complex set of assumptions about the planet's formation and evolution. Until we can peer more deeply into its atmosphere, this most fundamental question of its identity remains tantalizingly out of reach. Closely tied to this is the puzzle of its surface, or whether one even exists in a form we would recognize. If the water world hypothesis is correct, the surface might be the top of a global, superheated ocean, a seething interface between liquid and vapor under immense pressure. There would be no continents, no mountains, no solid ground whatsoever, only a perpetual, roiling sea fading into a steamy horizon. Conversely, if the planet is a mini-Neptune, it might not have a well-defined surface at all. The atmosphere could simply get progressively denser and hotter with depth, gradually transitioning into a supercritical fluid mixture that envelops a solid core with no sharp boundary between sky and ground. This ambiguity challenges our very definition of a planetary surface and forces us to consider worlds that are entirely fluid in nature, with no place for a foothold, no landscape to map, and no shore upon which waves could ever break. Then there is the enduring riddle of those obscuring clouds. We know they are there. The flat spectrum from Hubble is the direct evidence of their existence. But their precise chemical composition remains one of the most actively debated topics in exoplanet science. Are we looking at a global shroud of water droplets suspended in a superheated steam atmosphere? Or are these clouds something far more exotic, composed of crystalline salts like potassium chloride or zinc sulfide, condensing high in the atmosphere to form a permanent reflective haze? Some of the most speculative models even suggest the clouds could be made of tiny particles of silicate, a mist of vaporized rock that has risen from the scorching dayside only to condense out as a form of hot mineral fog. Each of these possibilities points to a completely different atmospheric chemistry and climatic history. Identifying the cloud material is not just about solving a cosmetic mystery. It is the key to understanding the planet's thermal structure, its weather patterns, and the very cycle of materials between its interior and its sky. Beyond these structural questions lies a deeper, more dynamic uncertainty concerning the planet's ongoing evolution. We observe that it has managed to retain a massive atmosphere despite the intense radiation and gravitational tides from its close orbiting star. This fact alone tells a story of resilience, but the details of that story are still being written. How quickly is its atmosphere actually escaping into space? Is it a slow, steady leak, or are there periods of more catastrophic loss triggered by the star's notorious flaring activity? The answer to this would tell us about the planet's ultimate fate. Is it slowly transforming from a puffy mini-Neptune into a denuded, rocky core? Or, if it is a water world, is it gradually losing its hydrogen and building up an abiotic oxygen atmosphere, fundamentally altering its chemistry over billion-year timescales? We simply do not have a long enough timeline of observations to see these processes in action, leaving us to infer the future from single, static snapshots in its immensely long life. These are not merely academic curiosities. The unresolved nature of GJ1214b makes it a critical test case, a benchmark for our entire understanding of a class of planets that is incredibly common in our galaxy but completely absent from our own solar system. Every unanswered question about this specific world represents a gap in our knowledge about the most typical type of planet in the Milky Way. Its mysteries drive the design of new telescopes, the development of more powerful supercomputer simulations, and the refinement of our theoretical models. It serves as a constant reminder that for every answer we find, the universe presents us with a dozen new and more intricate questions. This world, a hazy red dot 48 light-years away, continues to be a beacon for astronomers, not because it has revealed its secrets, but precisely because it has not. Its enduring enigma is a powerful catalyst for curiosity, ensuring that the story of GJ1214b is far from over, and that the next chapter of discovery is always just on the horizon. When we shift our focus from this single, mesmerizing world to the vast, star-filled canvas of our galaxy, the true significance of GJ1214b snaps into focus with breathtaking clarity. This isn't just the story of one peculiar planet. It's a vital clue in solving the grandest puzzle of all. What are the most common types of worlds in the universe? To answer that, we must look at the most common type of star. Red dwarfs, small, cool, and incredibly long-lived, are the true silent majority of the cosmos. They make up an estimated 70 to 80% of all stars in the Milky Way galaxy. For every star like our Sun, there are at least 3 or 4 of these dim red embers. For generations, our search for other planets was unconsciously biased. We looked for solar systems that resembled our own, centered on sun-like stars. But the universe, it seems, operates on a different default setting. The most typical planetary systems are not built around brilliant yellow suns, but around these faint, ruddy dwarfs. And the discovery of GJ1214b, a world with a thick, opaque atmosphere orbiting a red dwarf, suggests that the most common type of planet in the galaxy might not be a rocky sphere like Earth, but a shrouded, enigmatic world cloaked in steam or haze, much like the one we have been exploring. This realization fundamentally reshapes our understanding of cosmic demographics. Before the explosion of exoplanet discoveries, we had a tidy, if limited, classification system based on our own solar system's 8 planets. But GJ 1214b, a mini-Neptune or sub-Neptune, represents a category of world that doesn't exist here. The data from missions like NASA's Kepler telescope have confirmed that planets in this size, range larger than Earth but smaller than Neptune, are not rare anomalies. They are arguably the most frequently occurring type of planet we have found so far. They fill the galaxy, and when we combine these two facts, the prevalence of red dwarf stars and the abundance of sub-Neptune-sized planets, a compelling pattern emerges. GJ 1214b is no longer an oddity, it is a prototype. It is the closest and best-studied example of what is likely a galactic standard, a modestly sized planet with a substantial atmosphere orbiting the most common type of star. This transforms it from a fascinating case study into a crucial statistical anchor point, a Rosetta Stone that helps us interpret the fainter, more distant signals from thousands of its cosmic cousins. The prevalence of these thick atmospheres around red dwarf planets also speaks to the violent, chaotic conditions in young stellar systems. Red dwarfs are notoriously tempestuous in their youth, erupting with frequent and powerful flares that blast their inner planets with intense ultraviolet radiation. You might think this would strip away any nascent atmosphere, leaving behind bare, scorched rocks. Yet, the existence of GJ 1214b and many others like it proves that planets can form with, or quickly acquire, atmospheres so massive and dense that they can withstand this relentless battering for billions of years. This suggests that the process of planetary formation around these stars is incredibly efficient at gathering and retaining light elements, whether that's a massive amount of water ice from the colder outer regions of the protoplanetary disk that then migrates inward, or a primordial envelope of hydrogen and helium gas. A world like GJ 1214b, with its incredibly robust atmospheric shroud, demonstrates that a thick blanket is not a luxury in these systems. It may be a necessity for survival, a planetary defense mechanism against a hostile stellar environment. This galactic perspective forces us to reconsider the very concept of a habitable zone. We often define this zone as the region around a star where temperatures are just right for liquid water to exist on a planet's surface. But if the most common planets are not terrestrial worlds with Earth-like atmospheres, but sub-Neptunes with deep, opaque shrouds, then our traditional idea of surface habitability may be missing the mark for a huge portion of the galaxy's real estate. A planet like GJ 1214b orbits on the inner edge of its star's classical habitable zone, but its surface, if it has one, is far too hot for life. However, if such a world orbited just a little further out from its star, its thick atmosphere could provide enough pressure and greenhouse warming to maintain a vast, global liquid water ocean beneath the cloud tops, even if the surface itself remained inaccessible. This is the tantalizing concept of the Haitian world we touched on earlier. GJ 1214b, in its current scorching state, might be the overheated version of a planetary archetype that, in slightly more distant orbits, could offer vast, deep ocean habitats shielded from stellar radiation. This means the census of potentially life-friendly worlds in our galaxy could be far larger than we ever imagined, dominated not by Earth twins, but by steamy, water-rich planets orbiting dim red suns. Consequently, the intense study of this one world 48 light-years away is directly shaping the strategy for the next generation of life-finding telescopes. When astronomers draft the scientific goals for future observatories, like the Habitable Worlds Observatory currently in early planning stages, they are using the lessons learned from GJ 1214b. They now know that a significant fraction of their targets will be small, cloudy planets around red dwarf stars. The techniques developed to analyze its flat, featureless spectrum are becoming the standard tools for interpreting data from these future missions. The great challenge will not just be detecting the atmospheres of Earth-sized planets, but learning how to see through the veils of haze and steam that are likely to envelop so many of them. GJ1214b taught us that a flat spectrum isn't a dead end. It's a starting point for a deeper, more sophisticated investigation. It proved that we can study the atmospheres of worlds that actively hide their secrets from us, developing the analytical muscle we will need to one day identify the subtle, complex chemical fingerprints of life on a distant, cloudy world that, from our vantage point, is little more than a faint flicker in the light of a tiny red star. Our journey through the enigmatic mists of GJ1214b brings us to a moment of reflection, a chance to gather the astonishing insights we've uncovered about this celestial marvel. It all began with a subtle, rhythmic dimming of a faint red star, a whisper caught by dedicated telescopes that announced the presence of a new world. This discovery alone was a triumph, but it was merely the opening chapter. We learned that this planet is no ordinary sphere. It is a world defined by its atmosphere, a thick, opaque shroud that stubbornly guards its interior secrets. Whether this veil is a global blanket of superheated steam from a vast, churning ocean or a permanent, high-altitude haze of exotic salts and minerals remains the central, thrilling debate that defines modern exoplanet science. This single world, a hazy orb 48 light-years away, has become the archetype for an entire class of planet, challenging our Earth-centric views and proving that the universe's most common planets might be these mysterious, shrouded worlds orbiting dim red suns. The significance of GJ1214b extends far beyond its own bizarre conditions. It stands as a monumental milestone in our quest to understand atmospheres beyond our solar system. Its flat, featureless spectrum, first measured by the Hubble Space Telescope, was not a failed observation but a revolutionary data point. It taught astronomers that a planet's most interesting story can be hidden behind a global veil, forcing us to develop new tools and more sophisticated models to interpret what we cannot directly see. This world became a crucial testbed, a training ground for the analytical techniques we now use to study dozens of other distant, cloudy planets. It proved that we could push our technology to its absolute limits and still extract profound knowledge from the faintest glimmer of filtered starlight, setting the stage for the next generation of cosmic exploration. As we look ahead, the future of this mystery is brighter than ever. The James Webb Space Telescope and other upcoming observatories are poised to act as master keys, finally unlocking the secrets that have remained hidden for so long. With its unparalleled infrared vision, Webb will search for the subtle spectral fingerprints that will definitively distinguish a steamy water world from a cloud-obscured gas dwarf. It will hunt for narrow windows in the planet's oppressive haze, offering us a fleeting glimpse into the deeper, hotter layers of its atmosphere, where the true story of its composition is written. The answers are within reach, and they will not only solve the puzzle of this one world, but will also provide a foundational understanding for the countless similar planets we have discovered throughout the galaxy. The enduring lesson of GJ1214b is a celebration of cosmic diversity and the power of human curiosity. It reminds us that our own solar system, with its clear categories of rocky inner planets and gaseous outer giants, is just one possible arrangement in a universe teeming with infinite variety. The most common type of planet may be one for which we have no local example, a world that is neither truly terrestrial nor truly gaseous, but something uniquely in between. This steam planet, with its supersonic winds and potential rains of molten glass, is a testament to the raw, creative power of nature, crafting environments that stretch our imagination to its breaking point. So, as new telescopes turn their gaze toward this distant crimson world and countless others like it, remember to stay curious. The universe is revealing its secrets one strange, new world at a time, and the next great discovery, the one that will once again rewrite our textbooks and expand our sense of wonder, is always waiting just beyond the next star.